I think today we'll do a little bit different. So we'll kind of push through the rest of the material because we have a lot to talk about. And then tomorrow we'll do the review and then all the group assignments tomorrow. So basically we'll bring up all those. So that way we make sure we cover everything for the exam here. So good. Let me share my screen. Here we go. One announcement, I posted the solutions for the exam examples this morning. So those are now up there. So if you were working on those, then now you can check your answers. Again, reminder, don't forget, exam is Friday, so 2 days from today, and that's about it. So yesterday we were talking about Faraday's law. So again, we said that if I have a time-changing magnetic flux, so that's this portion here, that then induces a EMF or power source within inside of something else, so typically like a wire, which then has a resistance, which then induces a current, which then induces a magnetic field, and then that's equal to then, again, negative. That negative sign there is what we call Lenz's law, and the way that it's induced is then opposite to the direction of the change, times the number of loops times the net time-changing magnetic flux. Where again, magnetic flux is the magnetic field times the area times cosine of the angle between the two. So here, if I have, this is my magnetic field, this is my area vector, which again is perpendicular to the area itself, with magnitude equal to that of the area, then the angle theta is specifically the angle between those two guys. So this is what we call Faraday's law. And again, the interpretation of that negative sign is Lenz's law, which basically just says it happens in the opposite direction. So now that we know that, let's go ahead and do an example. So our first example says that, which is my first example, there it is. So this says that we have a loop of 100 loop square coil of wire of length L is equal to 5 centimeters and a resistance R equal to 100 ohms is positioned perpendicular to a magnetic field, which has a strength of 0.6 Tesla. So it says it is quickly pulled from the field at constant speed perpendicular to the magnetic field region where B abruptly goes to 0. So at T is equal to 0, the red edge of that coil is at the side of the field, or at the edge of the field. And it takes 0.1 seconds for the whole entire coil to be pulled outside of the magnetic field region into the non-magnetic field region. So once it's defined, the rate at which the flux is changing, the EMF and the induced EMF and the induced currents, how much energy is dissipated. So when that current is running through the coil, how much power is then being dissipated, so how much energy in this case, and then what is the average force required. So we'll talk about that in just a second. So basically, all this means is that, let's say here's my abrupt ending of my magnetic field region. So here I have magnetic field, let's say it's going into the page, and we know that this is what, 0.6 Tesla. And then this is my abrupt region, which means anything over here has 0 magnetic field. So there is no magnetic field on that side. Okay. So now what it's saying is that what, we have a coil. So here is my square coil. So all these have side lengths of L. And this thing is being pulled in this direction with a velocity V, where we want that to be equal to a constant. Okay. So then what it's saying is that T is equal to 0. So I'm going to draw this down here now. So basically what's happening now is that my square loop is now here at the edge of the magnetic field at T is equal to 0. So this is where it is at T is equal to 0. Okay. And then what it's saying is that it takes 0.1 seconds for me to pull the coil from this location now to fully outside of the magnetic field region. So now it's going to be sitting here. So the time it takes to go from here to here is delta T, which is equal to 0.1 seconds. Okay. Good. So what it wants to know then, again, are a whole bunch of different things. So part A, we want to know what is the rate of change of the magnetic flux. So this is part A. Good. So what is the rate of change of that guy? Good. So we know delta flux is going to be equal to the same thing as the final magnetic flux minus then the initial magnetic flux. So this is delta flux. So in this case, what's happening is initially there is flux through the coil because what? We have magnetic field going into the board or into the page. We have this loop, which has an area of A, where A is simply equal to the length squared because this thing is a square. So we know initially this thing has a flux because there's magnetic field lines which are penetrating the entire area. So this tells me that the initial magnetic flux is simply equal to the magnetic field times the area, which is then the magnetic field times the length squared. Now when it gets pulled out, what happens in that case then is what? Now there is zero flux, so the final flux is equal to 0 because now, even though there's the entire area which is still here, but now there's zero magnetic field penetrating inside of this loop, which means there has to be zero flux, because again, remember that flux is equal to B times A times cosine of the angle between the two. Okay? Now here, this angle is simply going to be equal to 0 degrees because the area, right? Remember the area vector is perpendicular to that of the area itself. So that means the area vector is either pointing in or out, but in either case, it's going to be 0 degrees. So that's why there's no cosine of anything here, because that cosine is simply 1. So here, we know our final magnetic flux is then equal to 0, which means our change in magnetic flux is then going to be equal to 0 minus B times L squared, which is then just simply equal to minus BL squared. So plug that in here. So then the rate at which the magnetic flux is changing, so delta divided by delta t, is then going to be equal to minus B times L squared divided by delta t. So it's going to be the same thing then as minus 0.6 Tesla times the length, which is 0.05 meters squared, divided by a change in time, which is 0.1 seconds. So plugging my numbers, what I get in this case then is, that works out to be negative 1.5 times 10 to the minus 1.5 times 10 to the minus 2. Flux has units of Webers, so this is a Weber per second. So this is my flux. Forget the negative 2 here. Yeah, good. Now, part B then is saying, so what then is the EMF? Well, we now know that the EMF is equal to minus the number of loops times the time changing magnetic flux. So the rate of change of that time of that magnetic flux. So it's going to be equal to negative 100, because that's the number of loops that we have, times minus 1.5 times 10 to the minus 2 Weber per second, which is then equal to plus 1.5 Weber per second, and Weber per second is actually the same thing as a volt. So this has an EMF of 1.5 volts. So Weber per second is equal to a volt. Units, squares. Okay. Good. It also wants to know what's the induced current. So we know that Ohm's law says that the change in potential, which in this case is simply equal to the induced EMF, is equal to the current times the resistance, which means that the induced current is going to be equal to the EMF divided by the resistance. We know the resistance was, what, 100? Is that right? Yeah, 100. So that brings us then to an induced current of 1.5 times 10 to the minus 2 amps. So that's my induced current. Was okay? Not too bad so far. Good. Part C then is saying, okay, so what's happening now is what? So let's draw. So if here is my boundary, so here I have magnetic field and here I don't. And let's say at some point, here is my loop, which is partway through. It's being pulled in this direction with a constant velocity of V. It now has current, which is running through it, right? So let's talk about the direction of the current, first of all. So what's happening here is if my magnetic field is pointing into the board, what's happening then is what? The flux is getting smaller, because what's happening here as I'm pulling this thing through, what's happening then is that the effective area, which has the flux going through it, which is now this area, is getting smaller over time. So what's happening then is that even though the magnetic field itself is not changing, but the flux is getting smaller. Now what Lenz's law says is that we have to induce a magnetic field in the direction opposite to the change. So what's happening here is since the area is getting smaller, I have to then induce a magnetic field, so be induced, in the same direction as the external magnetic field, since the external magnetic field is effectively getting smaller because the area is getting smaller. So what that means then is by right-hand rule number 3, I would point my thumb in the direction then of the magnetic field. My fingers would curl around in the direction of the current, which means that inside of this loop, I have a current which is then running in the clockwise direction. So this is the direction of my induced current. So as this thing is being pulled through, I now have an induced current which is running in the clockwise direction. That's going to be important for part D as well. So now we know is that what? Since this thing has a resistance, it has a current, it has to then have a power loss, where that power loss we now know is the same thing as the induced current squared times the resistance. So this is the power which is being lost. But it's not asking about the power, it's asking about the energy. So remember that power, by definition, is the change in energy divided by the change in time. Which means then that the change in energy, so the energy which is actually lost, is then going to be equal to the power which is lost times the change in time. So if I put all this together, this is then going to be the induced current squared times the resistance times the change in time, which is at point, pardon me, 0.01 seconds. So if I plug in my numbers, what I find in this case then is that the energy which is lost is 2.25 times 10 to the minus 3 joules. So this is then 2.25 times 10 to the minus 3 joules. Okay? Now, let's talk about part D then. So part D is now asking something about the force required. Okay? So let's talk about what's actually happening. So let's say I initially start off with a wire here, moving at velocity v. So if I just pushed it, what's going to happen? Well, if I push it, it starts moving through this region. I'm now creating, again, a current, where that current is moving in the clockwise direction, which means in this strip of wire here, what's happening then is we're creating a force. So remember that we have that the force on a wire is equal to the current times the length times the magnetic field times sine of the angle between the two. Or in vector form, this is going to be the current times the length crossed by the magnetic field. So here I would point my fingers in the direction of the current, curl towards the magnetic field, which is then into the page. So my thumb then points in the direction of the force. So this thing has a force where that force then is pointing in this direction. So it's going to be the direction of the magnetic force on that portion of the wire. Now there's also a force here which points this way. There's also a force here which points this way. But this force is the same as this force, so these two are going to cancel. But this one has nothing on this side to cancel it, which means that I'm going to end up with a force. Which basically means that if I took this coil of wire and I pushed it and I wanted it to go through this magnetic field region, well, as soon as it starts going through the magnetic field region, the current starts to flow, which means this portion of the wire starts to create a force. This force then is going to pull back in this direction, which means that this velocity is not going to be constant. Because now I have an acceleration, which means it has to slow down and it's going to stop. But the problem insists that this thing moves through with a constant velocity, which means the only way that's going to happen is if I grab this portion of the wire and I pull it in this direction with some external force. Okay. This is what it wants to know. What is the external force pulling on this wire to cause this thing to move through with the velocity equal to a constant? Okay. Well, if the velocity is equal to a constant, what's the acceleration? 0, good. So if it's 0, what's the net force? Also 0. So it has to be true then, is if I say this direction is positive x direction, then the sum of the forces in the x direction must be equal to 0, which means that the external force minus the magnetic force must be equal to 0, which means that the external force must be the same thing as the magnetic force. Okay? So this is then going to be the induced current times the length of the side, which is L, times the external magnetic field, times sine of the angle between the two. But here, the velocity is, or actually, sorry, the current is this way. The magnetic field is into the board, which means that those are at a 90-degree angle, so that's sine of 90. So here, theta is simply equal to 90 degrees. So here, the external force must be equal to simply the induced current times the length divided by the magnetic field, or it's the same thing as the induced EMF divided by the resistance times the length times the magnetic field. Look at my numbers. What I find in this case then is that works out to be about 0.045 newtons. 0.5 newtons. So this is the external force required to move this thing at constant speed. So again, the idea here is that once I'm moving it and the flux is changing, I'm creating a current. That current then creates a force, and I have to counteract that force because that force acts as a drag force. So this force here is actually a drag force. So this force is in the opposite direction of its motion. So I have to put an external force to make sure that this thing keeps moving. Good. Let's do another example. So the next example says that we're going to have a U-shaped wire. So here is my U-shaped wire. It says to make the rod in the figure below move to the right at constant speed, you need to apply an external, that should be force. Form, there we go. Force on the rod to the right. So once it's determined the magnitude of the required force, and then what is the external power needed for this thing to actually move. Okay. So here is my U-shaped wire. So here I have a U-shaped wire. This is a rod which is basically just sitting on top of it, and I'm going to pull it here to the right. So basically what's going to happen again is I'm going to create an EMF inside of my rod. We'll talk about why that happens in a second. And then the fact that it's on top of these conducting U-shaped wire, that's going to cause current to move through the system. So the current's either going to move this way or it's going to move this way. But what's happening here is, again, what's happening is this effective area here is changing. So initially, let's say this is at t is equal to 0, the rod is sitting here. This is my area, which then feels the flux. But as I start pulling the wire or the rod to the right, now this area here is actually getting bigger, which means that the flux is getting bigger. Since the flux is getting bigger, what that means then is I have to point my thumb in the opposite direction of that external magnetic field via Lenz's law, which then causes the current to move in that direction. So in this case, since my thumb has to go inward, my fingers have to curl around, again, in the clockwise direction, which means I'm going to have current running in the clockwise direction. So let's talk about this one a little bit slowly. So first of all, why are we creating an EMF inside of the rod? So let's look at just the rod. So here, this is my rod, and this is in an external magnetic field, which here is telling me is pointing out of the board or out of the page, and I'm moving that to the right with a constant velocity. So this is equal to a constant. So why am I generating an EMF? Well, again, this is the same thing as we know that the magnetic force on a charged particle is going to be Q times V cross B. So what's happening inside of here is inside of the wire itself, I have positive charged particles. So these are going to be my positive charged particles of Q. So what's happening then is since the rod is moving to the right with the velocity V, so are each one of these charged particles. So this charged particle is moving this way with velocity V, this one's moving with velocity V, this one's also moving velocity V. But since I have it in an external magnetic field, it then has to feel a force. So what's going to happen is as I'm moving it this way, I point my fingers in the direction of the velocity. Magnetic field is out, so I'm going to rotate my hand. So in this case, I'd curl my fingers in the direction of the magnetic field, which means these are all going to feel a force downward. So the magnetic force acting on each one of these is going to be downward. So as this rod moves, so now if it moves to this location, all of these charged particles then are going to start building up on this side. So all the positive charges are going to build up over here. But simultaneously, all the negative charges are going to build up on this side because all the negative charges are going to move in the opposite direction, which means that we're going to create an electric field inside, where that electric field then, what color haven't I used? We'll use black. There we go. Is going to point from the positive charges to the negative charges. So this is my electric field, which means that's what we're going to create a potential difference across this bar. So this potential difference is going to be the induced EMF. Now this will happen until Same thing that we talked about with the velocity selector. The magnetic force is equal to the electric force, which means then that we get a QV times B is equal to Q times E, which means that this guy's going to cancel with him, which means that the velocity then is equal to, again, the electric field divided by the magnetic field. So once that happens, then all of these charged particles on the inside will no longer feel a force due to the fact that the electric is equal to the magnetic forces. Now, how does that pertain to our question here? Well, what's happening here is now I have this rod sitting on top of this U-shaped conductor, which has a resistance R. So inside of here, I have a resistance R. So now what we're going to do is we're going to pull this in this direction again. We're going to build up a potential difference, which means that I'm going to get an EMF inside of the rod, and then that's going to cause current to flow. Again, here we have the magnetic field again is pointing out. So this is our magnetic field everywhere inside of here. Now, as we just said, what happens then is here, as this thing moves from this position to this position, and since it's moving at a velocity, this is going to be equal to that constant velocity times the change in time. So now if it moves to this location, what's happening then is that the effective area is increasing. So this is what we call motional EMF. These are problems which are called motional EMF. So what's happening here then is this EMF which is being generated then is going to be equal to the time rate of change of the magnetic flux is then equal to the induced EMF. Here I'm going to forget about that negative sign because I only want to know the magnitude of it. So this is going to be equal to the flux, which is going to be the B times the area. So the effective area here then is going to be the length of the rod. So let's say the length of the rod here is L. Times then the distance at which it travels, little l, all divided by change in time. So this is going to be B times the length of the rod times little l, but we know little l is the same thing as the velocity times the change in time, all divided by the change in time. The change in times are the same, so those are going to cancel. So it's going to be the same thing as B times L times B. So in this case, L is the length of the rod itself. So the distance between these two conducting rods. B is the magnitude of the external magnetic field, and V is the velocity at which it's moving. Okay? Now again, this is going to induce a current. My induced current, by Ohm's law, then is going to be equal to the EMF divided by the resistance. So it's going to be the same thing then as B times L times V divided by the resistance. Always okay? Okay. So now, again, what's happening is what? As we talked about, since the area here is getting bigger, we put our thumb in the opposite direction of the external magnetic field to counteract that increasing magnetic flux. Our fingers then have to curl around in the direction of the current. So we know in this case, our current is going to be moving in the clockwise direction. And this is going to be our current, I induced, which means through the rod itself, that current is going to be moving downward. So in the rod, we now have that there's going to be a force generated where we put our fingers in the direction of the current. Magnetic field is out, so we curl our fingers towards ourselves. Our thumb would point in the direction of the force. So in this case, our force that's going to be generated, color I haven't used yet, we use yellow, is going to be, again, in this direction. So this is going to be the direction of the magnetic force. Now, again, what I want is for this thing to move in this direction with a constant velocity v. So since I now have this backwards or drag force again, we have to do the same thing as before, which is go in and grab this rod and pull it in the direction that we want it to move to create the fact that it has a constant velocity. Same thing as before, since the velocity is equal to a constant, the acceleration must be equal to a constant, so the external force must be equal to then to the magnetic force. So we have the external force then is equal to the magnetic force, which is going to be equal to the induced current, times then the magnetic field times the length. So from here, we know the induced current then is going to be B times L times V divided by the resistance times B times L, which means the external force must then be equal to B squared L squared V divided by R. So this is the external force required to move the rod at constant speed. Okay? So the other part of the question then said, what external power is needed to move the rod? So let's go to a new page. Remember from 175 that power is equal to force, the magnitude of the force, times the magnitude of the velocity times cosine of the angle between the two. So this is power. Here, the power required externally is going to be the external force times the velocity times cosine of the angle between the two. But here, as we can see, the external force is in the same direction as the velocity, which means that the angle between the two is simply equal to 0. So this is just going to be the external force times the velocity. So that's going to be then equal to B squared times L squared times V squared, all divided by the resistance. So this is the external power required to move this rod at constant speed. Now, an interesting side question, which I didn't actually ask in the question, but I'm going to ask now, is how does that compare to the power lost? How does this power compare to the power loss? Well, we know the power loss is equal to what? The induced current squared times the resistance. We know that the induced current is going to be the same thing as B times L times V divided by the resistance, quantity squared times the resistance. So this is actually the same thing as B squared times L squared times V squared divided by R. So the power lost, as we can see here, is actually exactly the same thing as the power needed to pull this thing. So the external power, which is being supplied by that external force to pull it, is then being radiated away by the wire itself, increasing its thermal energy and then losing the energy via thermal energy. So my question, as a follow-up question to that, is, does that make sense? Does the power being supplied have to be the same as the power being dissipated? Does that make sense? Does that make sense that these two things are the same? What do you think? Katie was going to go for it and then change her mind.
Well, I'm thinking about our circuits, and
Okay.
I'm thinking for it to have a potential difference, it has to lose all of that on the way back around.
That's right. Just conservation of energy. That's right.
But then I was like, but that's with a battery, so maybe not.
Well, this is a battery, right? So when I'm pulling this thing, that's all you're doing. So when you're pulling this, you're creating an EMF, you're creating a power source, you're creating a battery. Exactly. So as you're pulling this thing, you are creating a battery, which means that, yeah, as you said, as you go around this thing, you have to have as much potential drop as you have increase. That's just conservation of energy. So this is actually just the loop roll. Exactly. So the rate at which I'm losing that power or that potential has to be the same as which I'm gaining by conservation of energy. So yes, this actually makes sense. That's exactly right, Kate. So this is just conservation of energy. See that? Don't doubt yourself. You're good. Okay. Is all right? So again, these are motional EMFs. These are, as far as the exam is concerned, these are typically our favorite types of questions that we ask, our motional EMF ones, because they're the kind of the easiest ones to actually ask. So again, here, what's changing is typically going to be the area. So again, here what's happening is this effective area is changing. So initially you have an effective area, but then it increases, and it increases by amount of VL or V delta T. That delta T cancels, so you're left with the EMF is just VLV. So, good. So next thing we're going to talk about is I got to put a page in the wrong spot. Oh, that's fine. So another interesting phenomenon about this is what's known as an eddy current. So let's talk a little bit about eddy currents. So what's an eddy current? So an eddy current is a current which is induced in a material which is typically not going to be magnetic. So this is a current induced in a material which is a non-magnetic material. Now, it can't just be any type of non-magnetic material. So here, it still has to be a conductor. So it still has to be a conductor. And the reason for that, again, is remember that for insulators, the electrons are so tightly bound in the insulator that they're not allowed to move. So to have a current, we still have to have electrons which are allowed to freely move throughout the material. So we still have to have a conductor. So it can't be an insulator. It still has to be a conductor. So not all conductors are the same. And so typically there are 3 different types of magnetic materials. There's what's known as a diamagnetic material, a ferromagnetic material, and a paramagnetic material. So here, you're specifically talking about something which is not a ferromagnetic material. So it's a conductor, but it's a non-ferromagnet. Your ferromagnets are the types which make your permanent magnets. So things like bar magnets, you know, your refrigerator magnets, things like that, those are ferromagnetic materials. So here we're talking about a conductor, which is a non-ferromagnet. So it's either going to be paramagnetic or diamagnetic. So let me stop sharing here for a second so I can kind of do my demonstration. So hopefully everybody can see this. So what I have here are 2 different types of materials. I have this, which is a PVC pipe. So this is basically just plastic. So this is my insulator. I have this one, which is copper, which I think is a paramagnetic material. So this is a non-ferromagnet. And then here, I have what are known as neodymium magnets. So does everybody know what a neodymium magnet is? It's basically the strongest magnet you can have that's a permanent magnet, okay? So here, you can see is that this is non-magnetic material. So this is plastic because it doesn't stick to it. This is also non-magnetic because it doesn't stick to it. Find something that is magnetic so you can see. So if I took this guy, which is our power source from the other day, put this on here so you can see, that makes a nice, very strong magnetic. So I can actually almost lift this thing up by how strong these magnets are, okay? So what is an eddy current then? So an eddy current is, if I took, first of all, this piece of PVC pipe, and I took the neodymium magnet and I drop it inside of it, what happens then is this thing falls to the ground at the rate of G, okay? But now, if I took the copper here and I do the same thing, so I drop this thing in here and I let it go, it takes a whole bunch more time for this thing to actually fall through, okay? So again, difference, take this one, drop it through, falls through at the rate of G. This one, let it fall through. Takes a lot of more time for this thing to actually fall through. Again, this thing is a non-magnetic material, but what's happening is as this thing is falling down through, it's actually creating these eddy currents. So what's happening is if I look at a ring of metal here as this magnet is falling through, what's happening then is that the flux through this ring here is increasing as this thing is falling down, which means that in this ring here, it's going to induce its own magnetic field in the opposite direction because the flux is getting bigger, which means the current is going to flow around in this direction, which causes the magnetic field to go this way, which then causes the repulsive force between this ring and the magnet itself. Because here the magnetic field is pointing this way, this magnetic field is pointing this way, that creates a repulsive force. Now up here, simultaneously, as this thing is falling down, in this ring here, the flux is getting smaller. So he actually creates his magnetic field in the same direction as this magnetic field. So this one is pointing this way, this one's going like this. So what's happening then is this one has current flowing in the opposite direction as what's going on here, but this is now creating an attractive force between the magnetic north this way and the magnetic south on this, which is causing it to be pulled upward. So as this thing is falling through, the eddy currents which are moving then inside of here, this one is causing a repulsive force, this one is causing an attractive force, which is causing this thing to slowly move its way down, which is why it takes much, much, much longer. So these are what we call eddy currents. So eddy currents are an induced current due to the fact that this thing is allowing current to move through in a typically non-magnetic material. Now, the eddy currents would basically go away if I took this copper and I cut slits in it. If I cut slits in it, what will happen in that case then is the current wouldn't be allowed to flow anymore and this thing would actually fall much faster. Eddy currents are used basically all the time. This is what creates a metal detector, basically. So when you go to the airport and you walk through a metal detector, it's actually taking pulses of magnetic fields and sending it from one side of the metal detector to the other side. And then what it's doing is when it goes through your keys, for example, inside of your keys, it's creating an eddy current. That eddy current then creates a magnetic field. So what happens is that pulse, which goes from one side to the other side, should take a certain amount of time. But due to the eddy current inside of your keys, that then creates a residual magnetic field, which then goes to the other side of the detector at a later time than what the other pulse went through. So that says that, hey, there's something metallic in here because there's an eddy current which is creating a residual magnetic field. So metal detectors that you walk through, or if you were using one on the beach, for example, these are all using eddy currents. Another use of eddy currents is actually in Japan, I believe. That's where they have the magnetic levitating trains. So those trains have no actual moving parts. So to actually slow that thing down, they actually create eddy currents with inside of the tracks. So you know that thing is what, sliding over top. You create then an eddy current inside, which then creates again that attractive force and repulsive force, which then causes the train to actually slow down and stop. So there's nothing on the track itself, which is grabbing the train, causing it to slow down. It's actually eddy currents with inside of the rails, which is causing it to actually slow down. Okay? So these are what we call eddy currents. We're not going to do anything mathematically with eddy currents. We just want to talk about. What's that, Katie?
It's a weird kind of question, but isn't this also what they use for magnetic braking and acceleration on roller coasters?
Exactly.
Okay.
Yes. Exactly. Exactly. Yeah, the same idea as with the train. It's still eddy currents, which are creating either repulsive forces or attractive forces or both kind of simultaneously. Yeah, exactly. Yeah, at least that way with the magnetic ones, you don't get the wear and tear of things actually cramping on, and so they'll actually last much, much, much longer. Good, so those are eddy currents. So next thing we're going to talk about is transformers. And not the movies Transformers, but actual transformers. So let's talk about transformers. So this goes back to, again, what happens if I create power at the power company, something we talked about a long time ago, and then I put it over a transmission wire, and then I try to send it to your house some distance away. So let's say here's your house, and then I want to see what happens if I try to go from the power company to your house. So let's say that the resistance then inside of the wire, so where am I looking? Here we go. So the resistance inside the wire, let's say, is 0.4 ohms. Your house is 10 kilometers away. That doesn't actually matter. And then you have the power company is creating electrical power at a rate of 120 kilowatt hour or kilowatts. Okay. So we want to know then what is the power loss in a transmission if we create 240 volts at the power company and then send that 240 volts across the wire to your house, or if we send 24,000. Okay. So again, here what's happening is the power company then is creating a power which is then equal to 120 kilowatts. We're going to go some distance. It says 10 kilometers, but it doesn't really matter how far it is. And that this has a 0.4 ohm resistor. And we want to say at point A, the power company is making a voltage, which is 240 volts. And we want to know what is the power loss by the time it gets to your house. And then for part B, we want to make then 24,000 volts. And we again want to know what is the power loss by the time it reaches your house. Cool. So basically, what's going to happen is what? The current, which is generated inside of the wire here, is going to be equal to, so remember that power delivered is equal to the current times the potential. Which means the current then is going to be equal to the power which is being delivered divided by the potential. So in this case, this is going to be equal to the 120 kilowatts divided by, in part A, 240 volts. Okay. So this is the amount of current. The power loss then is equal to the current squared times the resistance. So this is going to be equal to then the power which is being delivered squared divided by the potential squared times then the resistance. So for part A, this is then going to be equal to the power, which is 120 kilowatts, divided by 240 volts, quantity squared, times the resistance, which is 0.4 ohms. So this works out to be, for part A, where is it? About 100 kilowatts is being lost, which is about 80% of the power. So this is 100 kilowatts is being lost, which is roughly about 80% of the power. So that means by the time it goes from the power company to your house, 80% of the power which is being generated by the power company is automatically gone. Automatically. If you're making a voltage, again, of 240 and sending that same 240 across the wire. Okay. Now let's look at part B. So for part B, what's happening now is instead your power company is still making 240 volts, but then it's going to increase the amount of voltage that it puts through the wire to 24,000 volts. So in this case, the current then is going to be equal to 120 kilowatts divided by 24 kilovolts, which is a much, much smaller current, which means the power loss then is going to be equal to the 120 kilowatts divided by 24 kilovolts. So the kilo portion is going to go away, quantity squared times 0.4 ohms. Plug in those numbers, multiply all that out, and I get, if I remember right, 10 watts. So in this case, only 10 watts are lost by the time it reaches your house, which means that now that's less than 1% which is being lost. So now less than 1%. So in the case where if a power company only makes 240 volts and sends that 240 volts via direct current from the power company to your house, 80% of that power is going to be lost by the time it reaches your house. Basically nothing left, right? However, if you can somehow take that 240 volts, increase it by a factor of, 100 to make it 24,000, then the amounts which you're going to lose then now only becomes 10 watts, which is now 1% of the power being lost, actually less than 1%. So this is actually why we use AC as opposed to DC. Okay? So this is the reason why we started to use AC, even though way back in the day, there was this big battle between Nikola Tesla, who was a big proponent of AC power, and I think it was Edison, who was the person who was for DC. And then Edison actually took and killed an elephant using AC, and they talked about how bad it was and blah, 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 and it was going to kill everybody, and Armageddon was going to happen, and etc. if we used AC. But it turned out that we actually had to use AC to not have power loss. So Tesla was actually correct at the end, but you know, scientists are sometimes douches. So anyways, so this is actually why we use AC. So how do we actually do AC, and why do we actually use AC? So first of all, AC is actually created by the third way that we talked about yesterday of creating an EMF, which is actually by an angle which is time dependent. So actually what the power company does is it takes a coil of wire, rotates it in an external magnetic field at a constant angular velocity of omega. Okay. So here you have some sort of external magnetic field, say pointing in this direction. What happens? So the coil then is going to rotate. So let me kind of draw from a side view. So here you have the magnetic field pointing in this direction. And then let's say your coil at one moment is like this, right? So your area then is pointing off in this direction. So this is your area, where your area is changing because this thing is rotating in this direction with an angle of omega. So basically what happens is what? Initially, when I have this drawing here, where the area then is perpendicular to the magnetic field because it's straight up and down, you have zero currents going through. Now, as the area then starts to rotate, so as this thing starts to rotate, what happens then is the area is getting bigger, which means that the coil is going to induce a magnetic field in the opposite direction, since the magnetic field is getting bigger. So this is going to create a magnetic field in this direction, so it's going to be the direction to be induced, which is then going to cause the current to move in. So in this case, that's going to be in the opposite direction, until it reaches maximum, which is going to be when it's at 90 degrees. So when the face of it is pointing this way, or the area is pointing parallel to the magnetic field, and then it's going to keep rotating, in which case the area is going to start getting smaller. When the area starts getting smaller, it's going to induce a magnetic field in the same direction as the external magnetic field, causing the current to move in the opposite direction. So as this thing is rotating, what's happening then is the current is naturally switching back and forth due to the fact that at one moment, let's say magnetic field is this way, the coil is like this, there is zero. It's then going to start to rotate. So as it starts to rotate, the area is getting bigger, the current goes in one direction, reaches maximum, now reaches here, area is now getting smaller, the external magnetic field points in the opposite direction then, the induced magnetic field points in the opposite direction, current switches in the opposite direction, so this is actually what's creating AC. So AC is created by the fact of this thing simply rotating about a fixed axis, moving at a constant angular velocity. Now, depending on what country you live in, this angular velocity will be different. So we talked about this before, but for the US, this works at 60 hertz. For Europe, this is at 50 hertz. Actually, the frequency is, but so the rate at which this thing is rotating about will be dependent on what type of country that you're in. Now, why does this work for power transmission? Well, this works for power transmission because of what's called a transformer. So this is what's called a transformer. So a transformer is you have your primary. So what happens is you have the current coming in through a wire. That wire then gets wrapped around a ferromagnetic material. So this is iron. So this iron then will then transfer the flux, which is coming in here, to this side. Okay, so basically what's happening is what? The AC is generating a time-dependent magnetic flux inside of the ferromagnet here. Because again, I have wire coming in, this wraps around the iron. Since I have AC, that means the current is constantly changing direction, which means the flux is always constantly changing. So inside of these coils, I'm creating a magnetic flux. The fact that I have iron here, the iron then is to make sure that the flux gets distributed to this side of the transformer, meaning that the flux here is exactly the same as the flux here. On this side, this is what's known as the secondary, you then have coils which are wrapped around, which means that the flux which is happening here is the same which is the flux which is happening here, which means that you're generating now an EMF inside of these wires, which means that you're now creating a potential over here, which is now either going to increase from this potential or decrease depending on the type of secondary that you have, okay? So the whole point of the transformer then is to use the fact that the flux here is generating a flux here, which is then generating a power, which is generating a current on this side. If you were using DC, this could not be possible. So if you were using DC currents from the power company, that DC would have to be the same overall at every location. So whatever power you're creating or whatever potential you're creating at the power company has to be the same everywhere. But with AC, you're now using the fact that the EMF here is inducing an EMF here, which is the same flux here as here, which is then allowing you to now be able to increase the potential or decrease the potential. So basically what happens is you have two types of transformers. There's what's called the step-up transformer, which takes a small potential here and creates a very large potential over here. This is what the power company does just outside of their facilities to then create that 240 volts up to 24,000 volts. And then somewhere in your neighborhood, you have a step down transformer, which then does the opposite. So it takes the 24,000 volts and steps it down to 240 volts. So that way, by the time it enters your house, it's not too high a potential, so it's not going to kill anybody. So 240 volts is much safer than 24,000 volts. So, good. So basically, how does this work? So this works by here, you have a number of coils, which is called the number of primaries. Over here, you have a number of coils, which is called the secondaries, okay? So here you have a potential difference between the two sides, which is the potential across the primary. Here you also have a potential difference, which is the potential across the secondary. So let's write all those down. So the way the transformer works then, the transformer is that in the primary, you then have a potential difference of delta Vp, which is then equal to, so since this is an EMF, this is going to be minus then the number of primaries times the change in magnetic flux with respect to time. In the secondary, what's happening then is you have the change in potential across the secondary then is equal to minus the number of secondary coils times the change in magnetic flux. Now, again, what has to be true is that the flux here has to be the same as the flux here due to that ferromagnet or that piece of iron. So if I solve this one for the flux and I solve this one for the flux, we can then set these two guys equal to each other. So what this says then is that the negative change in magnetic flux, delta T, is equal to the change in potential divided by the number. And this side is the same thing, so minus change in magnetic flux with respect to time is then equal to the change in potential across the secondary times the number secondary. These two things have to be the same, so we can finally set these two guys equal to each other. So this then tells me that the potential across the primary divided by the number of loops of the primary has to then be equal to the potential across the secondary divided by the number of loops of the secondary. So finally, and this tells me that the change in potential across the primary divided by the change in potential across the secondary must then be equal to the number of loops of the primary divided by the number of loops of the secondary. So this is the way that the transformer works. Now, to get a step up potential, what that means is that you're looking at the ratio here. So basically, if I want the step up, which means that I want the potential in the primary to be less than that of the secondary, well, that means that I need the number of loops in the secondary to be greater than that of the primary. So for a step up potential, what that means is you need the number of loops of the secondary to be greater than the number of loops of the primary. That's what's going to create a greater potential. For a step down, to do the opposite, what that means then is I need the number of loops of the primary to be greater than the number of loops of the secondary. Now, what we also know by Ohm's law, right? Ohm's law says that the change of potential is then equal to the current times the resistance. Well, what this means then is that what? These two things should be opposite from each other, right? So if resistance stay the same, so that's also the same. Sorry about that. So what this says then is that the current in the primary divided by the current in the secondary is then equal to the number in the primary divided by the number in the secondary. So this is also true, because the resistance stays the same. So if I have the same resistance, if I increase the potential, then I have to increase the current. So let's use this. Let's do an example. Things I don't need. Stop bringing those up. We are you now. That one. Good. So here we go. So this says that we have a cell phone charger contains a transformer that reduces 120 volts AC into 5 volts AC to charge the battery, which is 3.7 volts. So suppose the secondary has 30 turns, and the charger supplies 70 milliamps worth of current. So it wants us to calculate the number of turns in the primary, and part B, the current in the primary, and part C, the power which is being transferred. So let's look at that. So let's draw everything. So here, what we know is what? We're taking the voltage across the primary, which is equal to 120 volts. And then we're reducing that down to the voltage across the secondary, which is then equal to, what was it, 3.7? Where am I looking? There it is. 5 volts, sorry. So we're gonna reduce that down to 5 volts, okay? And then here we know that the number of turns in the secondary was equal to 30. So for part A, we then wanna know how many turns are there in the primary. So, well, we now know that the potential across the primary divided by the potential across the secondary must be equal to the number of turns of the primary divided by the number of turns of the secondary. So this means then as the number of turns of the primary then must be equal to the number of turns of the secondary times the potential across the primary divided by the potential across the secondary. So it's going to be equal to 30 times 120 divided by 5. So plug in our numbers, what we should get in this case then is that this works out to be 720 turns. So in the primary, on the primary side, we have 720 total coils. On the secondary side, we have then 30 coils. Okay. Part B then wants to know, okay, so what is the current? So we know that the current across the primary is equal to the current across the secondary, which is then equal to the number of turns of the primary divided by the number of turns of the secondary. So here we're looking for the current in which one? The primary? Okay. So this says then that's what? The current in the primary is then equal to the current in the secondary times the number of turns in the primary divided by the number of turns in the secondary. Still feel like that's backwards. Yeah, that is backwards. This should be secondary. This should be primary. It should be secondary and it should be primary. Those two should be inversing. It should be secondary and primary. Okay. So this was what? 720, is that what it was? 700 milliamps. Okay. So this is then equal to 700 milliamps times then 30 divided by 720. So plug in our numbers, we found out in this case then is this works out to be 29 milliamps. 29 milliamps. Finally, part C, we want to know what is the power which is being delivered. So power, well, we know power is the same thing as the current times the potential. So here we can use the current in the secondary times the potential in the secondary, since we know both of those. So this is going to be 700 milliamps times then 5 volts. So plug in our numbers, we find in that case is that works out to be 3.5 volts. Okay. So this is kind of the main use of EMFs, at least inside of things that you're mostly familiar with, which is, again, the transfer of energy from the power company to your house, right? So this is actually why we use AC. So the point of using AC is to use the transformers, which then allows us to go to a much higher potential. That much higher potential allows for less power lossage because the current is much smaller and the potential is much greater, which means that as it's being transferred from the power company to your house, it minimizes the amount of power which is being lost. Okay. So this is actually the real reason why we use AC. DC, again, will not allow that to happen because this only happens because we have a time-changing magnetic flux. If we're using DC, we couldn't have a time-changing magnetic flux anymore. Good. So the last thing to talk about in this chapter, so we'll have to finish off some of this tomorrow, is what's known as inductance. Inductance. So inductance happens inside of circuits. So there are two different types of inductance. The first one is what's known as mutual inductance, and the second type is what's known as self-inductance. So let's talk about each one of these guys. So let's talk about self-inductance first. So the way self-inductance works is, let's say I have a battery connected to a solenoid. So as we talked about yesterday, so a solenoid is a coil of wire, which is then connected to, say, something like a resistor to make sure that we have current flowing through our system. So there's going to be some EMF. So what's going to happen? So what will happen is, as soon as I turn this on, I'm going to have current flowing through due to the resistor. Oh, I just wrote current as R. So what's going to happen then is I'm going to have current then start going through this solenoid. But what happens is, as the current starts moving through the solenoid, I'm going to then have a magnetic field due to the fact that my current's moving through, so I point my thumb in the direction of the current. In this case, my magnetic field would curl around, which means that, so in this case, it would curl in this direction, which means it would go into the page anywhere along here. So what's going to happen here then is I'm going to create a magnetic field at this location pointing into the board, or into the page. Now, what will happen is, since the current has now started, I'm now going to have a time-changing magnetic flux due to the fact that I now have a magnetic field from this current pointing into the board. Right? Initially, there was no magnetic field. Now there is a magnetic field, which means I have a time-changing magnetic flux. Since the current is getting bigger due to the fact that it went from 0 to non-zero, that means this magnetic field is getting bigger, which means that each one of these coils then will create an EMF and create an induced magnetic field which points in the opposite direction. So B induced then is going to point in this direction from each one of these individual coils. Now, what that means then is that this is going to induce a current due to the fact that it's inducing an induced EMF in the opposite direction at which this current is moving. So I'm going to induce a back current, is what this is called. So this is the direction of the induced current, which is equal to what's known as the back current, which is creating what's known as a back EMF. So I also have a potential, which is being created in the opposite direction, which is what's known as a back EMF. So basically what happens is this current is trying to move through in this direction, but this is inducing a current in the opposite direction, which means the sum total current, which is moving through this inductor or the solenoid and throughout the rest of the circuit, is now going to increase over time as opposed to go from 0 to maximum instantaneously. Okay? Which means that what's really happening is I get a potential difference then across this inductor, which is what we call the back potential, which is then going to be equal to negative the L times then the current, okay? Sorry, change in current over change in time. There we go. So L here is what's known as the self-inductance. So this is self-inductance. So what happens is when I turn on this power, I get a current in the opposite direction, which causes it to take its time to increase going from 0 up to its maximum amount of current. Okay? Now, if I do the opposite, if I had current running through there maximally and then I turn it off, what happened in this case then is this current is still moving in the same direction, but it's getting smaller over time. So the direction of this induced magnetic field will be in the same direction as the magnetic field here, which means the induced current would be in the same direction as this current, which would cause it to go to 0 much slower over time as opposed to instantaneously. So this is what we call the self-inductance. So this thing is feeding off of itself. It's either hindering itself when I'm trying to charge it up, or it is keeping it going when I'm trying to shut it off. Okay? So this is what's called self-inductance. Mutual inductance is now when I have two circuits. So let's put one circuit here with an inductor. And then I have a secondary here, which has another inductor. So here what's going to happen is now I'm going to have currents running through this circuit. So this circuit is going to have current running in this direction. So let's call that I1. Actually, here, let me take away the battery. We don't need the battery over here. Stop it. So let's take away that battery, just for funsies. So here I have the current, which is going through. That current then is going to start moving through here, which is going to cause this current then to increase slowly over time due to the self-inductance. But here, if my current's going in this direction, I'd curl my fingers in this direction, which means over here, I'm going to create an external magnetic field. Oops, sorry, which is pointing out of the page at all locations. So this is my external magnetic field. Since this is getting bigger, what that means is we have to induce our own, each one of these coils then is going to induce its own magnetic field and in the opposite direction. So it's going to be the induced, which means he's going to create his own current then in the opposite direction, which means he's going to induce a current inside of himself going in the opposite direction. Okay. But since this thing is creating a magnetic field going this way, so that now on this coil, this is now creating a magnetic field inside of each one of these. This is going to be B2. This would be B1. This is now going to create a back EMF inside of him, which is also going to be the opposite direction, which is going to cause this current to change much more slowly over time. So as this current changes, that creates a current inside of here. This current then simultaneously creates another current inside of here, which is what we call mutual inductance. So these two are feeding off of each other either in a positive way or a negative way, depending on if I'm trying to charge the system or discharge the system. So this is what we call mutual inductance. So let's talk about mutual inductance. Make sure I get all my stuff right here. Hey, come back here. So for mutual inductance, we then say that what? Let's look at this system here. So here we would say the number of turns here in this solenoid times the flux through that solenoid, which is the flux in the second due to the first, is then equal to the mutual inductance of the second from the first times the current from the first. Simultaneously over here, I then have the number of turns in the first times the flux in the first by the second, which is then equal to the mutual inductance from in the first by the second times the current from the second. Now here, if I look at how each one of these changes with time, then I can say the number in the first times the change of flux in the first by the second, then must be equal to the mutual inductance in the first by the second times the change in current in the second from the second divided by time. Here, then I get the number of turns in the second times the flux through the seconds with respect to time, then is equal to the mutual inductance of the second by the first times the change in time of the first currents. Now, the induced EMF inside of here, E1, is going to be equal then to, since this is actually EMF, then I would just divide both sides by N. So finally this thing would be, so you remember that EMF is equal to N minus N times the change in flux with respect to time. So this is then going to be equal to minus the mutual inductance M12 times the rate of change of the second current. And on this one, the induced EMF is then going to be equal to minus mutual inductance to 1 times the change in current from the first with respect to time. Now it turns out that mutual inductance only depends on geometry. So basically it says that what? The mutual inductance here only depends on the geometry between these two inductors, which means that this M12 here is exactly the same as this M21 here, because it only depends on the geometry. The geometry is exactly the same. So finally, we can simply write this as EMF1 is equal to minus the mutual inductance times then the change in current of the second with respect to time. And then this one says that EMF2 then is equal to minus the mutual inductance times the change in current of the first with respect to time. So this is now what we call mutual inductance. So again. Everybody's okay? It's kind of a lot. Okay, so let's do an example of mutual inductance. So this says we have a long, thin solenoid of length L and cross-sectional area A contains N1 closely packed turns of wire. Wrapped around it is an insulating coil of N2 turns. So assume all the flux from coil 1 passes through coil 2 and calculate the mutual inductance. So let's draw what's happening here. So basically what's happening is what? I have my small, thin solenoid here. So if I looked at it from the front view, this has a cross-sectional area A, and this has a length of L, and it has number of turns N1. Wrapped around that, I now have a larger solenoid, which then has N2 worth of turns. What we want to know then is, again, what is the mutual inductance? So let's go back to what we wrote down. So we now know that what? The number of turns of the first times the flux in the first by the second. Actually, no. So here we want the second one. Let's do the second, not the first. We're going to look through the flux going through the second. So we have the number of turns of the second times the flux through the second by the first is then equal to the mutual inductance times then the current from the first. So what this tells me then is that the mutual inductance, whoops, too many rolls on my M, there we go. Mutual inductance then is equal to the number of turns from the second times the flux through the second by the first divided by the current from the first. So this is my mutual inductance. Now lawn mowers driving me nuts. Okay, everybody's okay? So now we just have to calculate the flux through the second. So flux through the second by the first. So this is then going to be equal to what? So let's look at what's happening. So here is our small coil. Here's our large coil around the outside of it. Now remember that, as we talked about yesterday, a solenoid has a magnetic field which only passes through the center of the solenoid, where that solenoid has a magnetic field which was equal to mu naught times little n times the current, which was then equal to mu naught times the number of turns times the current divided by the length. This was the magnetic field. So here we know that what? The magnetic field in the second one, because the outside one is the second one, is then simply equal to the magnetic field from the first, times the cross-sectional area, which the cross-sectional area in this case is simply that of the little one, right? Because it's not getting all of the magnetic field through the entire thing, it's only inside of this little tiny area here. So phi 2, 1 then is going to be equal to the magnetic field of the first times then the cross-sectional area of the first, or that little one. Now using this is going to be equal to mu naught times the number of coils in the small one, because that's 1, times then the current of the first one divided by simply its length. Now let's put that in here. So this is now going to be equal to N2 times mu naught times N1 times the current I1 divided by L times I1, or the two I's are the same. So this now becomes simply mu naught N1 N2 divided by the length. So this is then the mutual inductance for this particular situation. Okay. Now, for self-inductance, has exactly the same type of structure for mutual inductance, which is then equal to negative of what's known as the self-inductance times the change in current with respect to time. So we'll pick up from there tomorrow. So we'll do an example for self-inductance. And then the last thing to talk about is the fact that, as we mentioned before, the inductor, or the solenoid, which is also known as an inductor, is the magnetic analog of the parallel plate capacitor, which means that it's point is the store energy, which in this case, it's going to store energy in the fact that it takes work for it to go from 0 current up to maximum current. Because again, as the current is starting to build up, there's that back current, which is pointing in the opposite direction, which means it has to do work to overcome that back current to go from 0 current all the way up to maximum current. So here, the energy then is going to come from the fact that it takes work to store it, so that work then is going to be stored as potential energy in the current itself. Just like the capacitor took work to go from 0 charge up to maximum charge, so the work was stored as potential energy via the work it took to increase it from 0 charge up to maximum charge. So we'll talk about that tomorrow. It's basically going to have exactly the same structure. So we'll do an example. We'll talk about how that thing stores energy, and then that's basically it. So we'll be done. So we only need maybe about 10 more minutes tomorrow, and then we'll do a quick review, and then I'll basically have a whole bunch of different group assignments. We'll talk about each one of those, and then I'll let you work on those for the rest of the time tomorrow. Okay. So sorry, all that was kind of quick. Was there any questions anybody has? Any confusion? I know I kind of talked a lot. Katie talked every once in a while, so it was fine. It wasn't just me. So it was fine. So everyone doing okay? Not too bad? Okay. So otherwise, then I will see everybody tomorrow. So don't forget, no lab today. If you want to talk to me during the lab time, my wife has an appointment at 11, so I'll be with the kids. But just send me a message and I can come on to Zoom and talk to you about that. Otherwise, I'll be trying to write your exam for Friday, so it'll be great. Okay. All right. So if there's no questions, then I'll see everybody tomorrow.